Okay, welcome to this lab instructions in here. This is for the lab E over M. This should be a quick introduction to this lab. The purpose of this lab, again, as you can clearly see from the title in here, is to basically find the ratio of E over M. We're going to be using Lorentz force for electrons that are basically shot through a region where there is a magnetic field. And the ratio of E over M we can clearly see just by the ratio of the known mass of the electron over and that of the its charge. It should be this number. So we're going to take this number as given and we're going to compare our results to it. So again, this is typical stuff, name, all of that. So this is the apparatus actually that we'll be using. We're going to be using three different basically voltages in this case. A voltage to basically heat and the filament enough so that the electrons are freed from it. Another voltage to accelerate them. And the third voltage is actually to run current through these coils. And that current should be big enough, basically strong enough, to generate a magnetic field, and we should be able to find that magnetic field. So those are the three knobs that basically you'll need for a typical lab like this one. We're going to get a reading for the current. We're actually going to adjust the voltage in such a way that there is actually the voltage across the coils themselves, where there is a magnetic field, so that the current is specifically fixed at specific values. The voltage, though, the accelerating voltage, the second voltage, I'm going to show you the apparatus, the diagram, the schematic of how it looks like quickly, need to be basically, technically it should be fixed, but we will see that it's going to fluctuate. So this V is going to be the reading from that. So again, when there is no electric field, basically this is how much we know. And if there is a magnetic field, and if the velocity is perpendicular to the magnetic field, that these electrons will spiral, and this is the Lorentz force that is going to basically give me the ratio of E over M. All I have to do is, because I have a sign of 90 degrees in here, and this is a centripetal acceleration because they are spiraling. So in this case, basically, this is the ratio of E over M. It has to do with that velocity with which the electrons enter the magnetic field divided by the radius of this curvature times B naught. If I can find V, if I can B naught, if I can find R, I'm in business. So once the electrons enter this region where there is a magnetic field, there is actually another expression that I'm going to use. This is how much they accelerated actually. Okay, first of all, I'm going to come back to the apparatus quickly. Okay, so initially they were at rest, so they gain a kinetic energy 1/2 of mass times the velocity squared is equal to the potential energy in this case, which is the charge of the electron times the potential, the electrical potential. From here I can also have another expression for the velocity, so which also involves E over M. If I take that expression and put it back into this expression in V, so now I have an E over M in here, and I have square root of E over M in here, square both values, and at the end I will get this expression for E over M. So it has to do with the delta V, the voltage that accelerates the electrons. It has to do if I can measure the radius with which this thing are spiraling. So I'm in business. And if I know how to calculate the magnetic field, then I'm in business. So those are this is basically the essence of the whole calculation here for this lab. So let's go to the apparatus again. There are three power supplies. Actually, there is one that is not shown, and I'm going to talk to you about it quickly. So you have one in here that heat up the filament hot enough so that the electrons are immediately freed up from it. Then they are accelerated, actually, the electrons, by another voltage through this direction. So you apply a positive voltage in here, a negative voltage in here, so the electron will move to it. There is a grid actually that can only, the grid is used for collimation, so that only a beam of light is going to come out of it. So now imagine that you have accelerated electron coming straight through, shooting through in a region where there is a magnetic field. Okay, here is how the magnetic field look like. It's actually two coils, okay, and I need two, and I'll tell you why I need two of them, of radius A for both of them. And we can find the magnetic field due to a coil because they have a number of turns in here. Each one have the same number of turns. Both of them are symmetrical. So the magnetic field that we calculated in class to do a single turn, so n is equal to 1, was actually given by this expression. Okay. Now if I have n of them, this is the expression for that. But if I have two coils and I go to the middle, so Z is somewhere in a position between them, and the middle between them, this is basically, I shift the origin in this case so that the origin actually is in the middle. So this expression is true everywhere, not just in the middle. Okay, I have one to the left, one to the right. That's why I have Z plus D and Z minus D in here. this expression has peculiar behavior. This expression itself, depending on how I choose D versus A, I can get different behavior for the magnetic field that is between them. If the ratio is not exactly correct, the magnetic field will be too picked in the middle and then drops rapidly. So if the electrons start to deviate from the middle, they will see different values of the magnetic field, and this expression will not be useful to me too much because B naught is changing a lot. Same thing, if the ratio is too little in this case, also actually is going to increase and then start to decrease, and again the magnetic field is not uniform. There is specific value for that ratio that gives me that's why I need two of them to give me a whole region where the magnetic field stays constant. Okay, using Taylor-Maclaurin expansion for this basically B, the magnetic field is a function of how far we move from the center. We will find it to be given by this expression. This is Taylor series basically. Because this function is actually even in Z, you can show that B1 and B3 are 0, and any odd term in here due to the odd derivatives are 0, and the even derivatives are non-zero, but you're going to choose this one so that it's 0. Okay, then in this case the magnetic field basically will be given by B naught and will be constant more or less for large values. You have to pick up the Z to the power 4 before you get any significant contributions, and that is what the whole analysis is in here about. Okay, so if you make B2 so that you choose D is equal to half of A, then you're in business. Okay, then B2 is 0, everything else is 0, so you answer these questions, and that is the value of B naught when everything is chosen correctly. One thing in here, so we have B naught now as a function, or the magnetic field as a function of the current. So if I vary the current in the loop, so I know exactly how much it is. N is fixed. N is 190 turns. The radii in this experiment are 14 centimeters. Okay. Now A is fixed. In this expression, you're going to use a CGS system, and the CGS system, the distance is actually in centimeters, the mass is in grams, and there is no mass in these whole expressions, and the time is in seconds, the currents are in amperes, so the value of I stays in amps, and the N is given to be 190, A is 14, and mu naught is actually 1 in the CGS system, so do not replace it by 4 pi 10 to the negative 7. If you're interested to change everything to MKSA, you're fine, okay? You can, but you can keep everything the way in this unit because everything is going to come out in Gauss, and the magnetic field is going to be in Gauss, not in Tesla, as I said. So we have everything in here for this lab. We have B naught from the current. If I can measure now R, because delta V is coming from the voltage, by the way. So if we can find R, we're in business. So how can we measure R? Is by looking through. There is a hole actually in the whole apparatus where you look through it and try to estimate on one side what is the position on one side of the beam and what is the position on the other side of the beam, and the difference between them is actually the diameter. Divide that by 2, so they're called L1 and L2. Once you take the difference and divide it by 2, you have the radius R. So you're in business now. You have everything you need for this lab in here if you can find all of these expressions. Obviously, we don't have the hold on, let me find we don't have the let me start a new session here. Okay, so let me go back into where I was. So let me open the link in here, because if we're going to connect these things in here, we're going to do it in actually lab. So this is basically what I was talking about, the radius. Okay, so let me go to the link now and start filling this table. So this table will get the delta V's, because they were supposed to adjust it between 125, 150, 175 and 200 volts. That delta V, the accelerating voltage. The currents are fixed, chosen so that they have these specific values, 5 values for each voltage range, for each accelerating voltage range. And at each point we're going to get L1 and L2, and L on one side and L2 on the other side, and we're going to find them. Once you collect your data, you're supposed to take it to this Excel file which is provided for you. The Excel file will actually complete the rest of the calculations for you. So let me go back into that link, okay, to collect my data. So right now I don't have anything. Okay, so I'm gonna change the voltage to 125. This is what you would do. Okay, once you have the voltage 125, we're gonna collect the data. Okay, so we have L1, we have L2, we have the voltage 125.44 for the current of 1 amp. We have L1 and L2 again for a voltage of 100. So all of these voltages are around 125. Again, because you adjust it to 125 and the current starts running, so it may go up and down depending on the sensitivity of the device. Okay, so you need to report this data back to your table. You have the currents in here that are fixed, they don't change, and you have the different L's and L2. Now, if you are interested to find the next set, which is 150, so this is increments of 25 volts, don't forget to collect the data in here, okay? Because you should do that in the lab too. So when you change the voltage, things change and the current might change, so you need to adjust everything and get your readings done. In the lab, actually in the practical lab, you're going to actually change the currents so that it is fixed, and each time you change one of the currents, you're going to get different values in here that you need to actually go and look and peek and see if you can find them. Once you have that data, basically you're in business now, because you have all of these tables filled for you. You're going to open that Excel file and fill it. Once you open the Excel file, it should give you all of these values in here. Now, you're supposed to also go to this link. Okay, I'm going to copy the link. I'm going to go back to the same tab in here, the same page in here. I'm going to open a new tab. Okay, and in here, since it's the location that was given to me, it's that of the GPS coordinates of Norco College. You can copy these coordinates and place them in this location, or actually look for it by address, which is the same thing. Okay, use the address location in here and find the GPS coordinate, but you have to know the altitude. The altitude defaults in kilometer. Make sure you change it to feet, because that's how it's reported in the United States. So once you have these values, basically make sure also that these are checked correctly. You have north and west, or whatever. We're in northwest, so we don't have to change that. Anyway, once you have that, you're going to be given once you click calculate, you're going to be given the values of the magnetic field for the Earth, due to the Earth, because what you want to do is check whether or not the magnetic field of the Earth will have an impact on your reading or not. Okay, and then if the errors will improve or not improve or something like that. This is what we do in the lab, but this data is actually provided to you, so maybe you will find a lot of errors and blame it on the simulator that doesn't really simulate your location where you are at, or where Norco is at. Actually, I didn't really honestly do the actual lab in Norco College to see exactly if my data will match it or not and simulate that location. So anyway, you're gonna put that back into the Excel file, and you have to follow these steps in here to get the solver. And you need, once you click the solver, you need to check all of these things in the solver, and it's going to tell you whether or not these errors are good enough or not. Okay, so that's basically in a nutshell what your lab is. I hope this video was helpful for you, and if you have any questions, please let me know. So I'm going to stop the recording quickly in here.